Greetings and welcome, friends, boys and girls, math fans of all ages. We're here in Chapter 9 today. We're talking about right triangles throughout this chapter. And, of course, we're going to start with the classic, the Pythagorean Theorem, which is something that you guys already know is probably some 7th or 8th grade standard. I don't know. But here we go. It says, Pythagorean Theorem. In a right triangle, the square, which they're talking about the math. We good? All right. Mathematical operation, not the shape. The square of the length of the hypotenuse, okay, what, which is actually the same as if I built a square off of that hypotenuse as its area, is equal to the sum of the squares of the lengths of the legs. All right, so classically known as a squared plus b squared equals c squared. All right, so in terms of Pythagorean theorem, like I said, you've seen that before. Some potentially new terminology is the Pythagorean triple. All right, Jack, I don't know if you knew this one. These are special sets of numbers. A Pythagorean triple is a set of 3 positive integers. All right, keyword integers, a, b, and c, that satisfy the equation a squared plus b squared equals c squared. Now, does anyone know of a Pythagorean triple? Aha, right? 3, 4, 5 right triangle is absolutely a Pythagorean triple. That's a pretty common one. And multiples of those will also be Pythagorean triples. So if I scale that up, that will also work. So notice, here's some classic Pythagorean triples. It's been a while. I probably knew this one and this one. That one's familiar. I would have known there was a 24, 25. I would have had to solve for 7. And then the multiples of those create entire families of Pythagorean triples. These aren't the only types, by the way. Yeah, there are other ones. But these are common ones. And it's nice having a triangle that happens to have integer sides because hooray for integers, am I right? Yeah, we like integers. Whereas typically other triangles are going to have some sort of irrational number, a square root within them. But if you're familiar with right triangles, you might be able to actually solve these problems pretty quick if you know some of the Pythagorean triples. So for instance, this one, it says find the value of x and then tell whether the side lengths form a Pythagorean triple. All right, so let's just do the classic Pythagorean theorem here first. So A, I'll call 5, B, I'll call 12, I'll leave that as x, and according to the Pythagorean theorem, I would say 5 squared plus 12 squared is going to equal x squared, so that's 25 plus 144 is equal to x squared. Add those together, that's 169 equals x squared. And how do I solve for x? Root both sides. And algebraically, you get plus or minus. All right? So you get positive or negative 13. Algebraically, there are 2 answers to this equation. Geometrically, there is only one, because we do not consider negative dimensions to make that much sense. All right, so geometrically, it's just the positive. And actually, the square root symbol is a Greek symbol that literally would mean what is the side length of a square with this area. And so the symbol in its original context only would have meant the positive version, but algebraically to this equation, there are 2 solutions. Question, comment, observation, yeah. Oh, that was QED, like this, right? And then another symbol was like 3 dots, like the predator, and that was like a therefore. But those, I don't know. There's all sorts of little things. All right, let's see. Let's apply the Pythagorean theorem when we already knew the hypotenuse, because algebra works in all sorts of directions. Hooray for algebra! All right, use the Pythagorean theorem. So, Pythagorean theorem, by the way, only works for right triangles. Let's just make sure we're aware of that. only works because I happen to have a right angle, and by right definition of right triangle, it's a right triangle. Find the value of x, and so here we go. So I'm going to have a is equal to the 7, c is equal to 14. How did I know this was the c? How do I know it's the hypotenuse? Ah, because it's opposite of the right angle. Okay? I mean, you can kind of tell just by scale, but I just wanted to point that out. We already knew that. And the x is my unknown. So when I plug this in, I'm going to have x squared plus 7 squared equals 14 squared. And now we just solve. X squared plus 49 is equal to 196. Thank you, with the save. Subtract 49. Gentlemen, don't get distracted with little strips of paper. X squared is equal to 147 when I subtract those. How do I get x by itself? Root. Both sides. Plus or minus. Don't forget it. Now, technically, as a geometry teacher right now, it'd be fine if you forgot the minus sign. But as an algebra teacher, and your Algebra 2 teachers will thank me, always remember the plus or minus. Your pre-calculus teacher, your calculus teacher will thank me if I make sure you remember the plus or minus there. And so the square root of 147, yeah, you could get a decimal approximation. In this case, that is a radical that can be reduced. It turns out, and I wouldn't have expected you guys to know this, but the square root of 49 fits into that 3 times. And what's so great about the square root of 49? It's 7. So plus or minus 7 rad 3 is x, right? And so my answer for x is going to be 7 square roots of 3. Oh, wow. This is actually a special right triangle. Did you know that? Later on, we will know that this is a 60-degree angle and this is a 30-degree angle. And I specifically knew that because of these ratios. But don't worry about that right now. All right, this is like a spoiler right there. And if you wanted a decimal approximation, which obviously for like a word problem, real-life application, you could type in the square root of 147 on your calculator. You could have done, right, 7 times the square root of 3, and you would have been able to get that as well. All right, ooh, here we go. Speaking of real-life problems, bless you, yes. Question? How do you square root? Yeah, you do second, and then it's right above the square button. You got it? All right, cool. The skyscrapers shown are connected by a skywalker. Wow. What just happened? Whoa. A skywalk. Wow. All right. Yeah, Rogue One. Spoilers. All right. Use the Pythagorean Theorem to approximate the length of each support beam. So here's our support beam. Like that. And if I want to find that length, what could I do? What are our thoughts? With what numbers? I disagree. Whoa, man. My computer is like bogging. We are. Not live, but half of 23.26. Oh, wait, you might be right. Oh, I'm going to accept your rightness. I withdraw my original wrong conclusion. I thought they already gave us the full length of the sky bridge. 23.26. B is going to equal 47.57. And let's find the value of x. You guys know how this goes. X squared is equal to a squared. Right, Lauren? Plus b squared. Right. And so that's definitely some calculator numbers there. Wow, they just skipped right to the end here for me. I'll tell you what those numbers are. 23.26 squared is 689.59 when I round to two places. 47.57 squared is the 2,262.90. Yeah, that would be crazy sauce. Add those numbers up, and what do I get? I got, oh, why did I write x squared plus? X squared equals 2,952.49. And now what would I do to solve? Root both sides. Plus or minus, don't forget it. And I would get x is approximately plus or minus 52.95. Okay? So yeah, then I can get the length of those support beams. And that's 52.95 what? And those are lengths. It's not area, correct. Okay, let's, oh, guys, this gets interesting. What about the converse of the Pythagorean theorem? Now, Pythagorean theorem is probably familiar to you, but the converse, perhaps not. I don't believe you've seen this. But it turns out that if the square of the longest side of a triangle is equal to the sum of the squares of the lengths of the other two, right? Right? Then the triangle is a right triangle. So you can use the converse, the Pythagorean converse, as a test to determine right triangleness. Sure. All right. So let's see. If I want to determine whether or not this is a right triangle, the thing that I consider my hypothetical hypotenuse must be the longest side. Whoa, for the longest side. Wow, that's pretty good. So, Lauren, what is the square root of 113 squared? What? Actually, we'll watch this. Schwink, schwink, right? That's just 113. 113. So, right, Aiden, you with me? You with me, Aiden? So 64 plus 49, that is actually 113. So that means that this is a right angle, and the reason why is the converse, the con-Pythag. How about that? Good stuff. What about what? Oh, no, I feel like that would be getting the converse of the Pythagorean theorem. I don't know. I feel like those letters belong to CPCTC. And saying Pythag is so cool. Like, one of you guys are going to go home and make PythagCon your gamer tag. Yeah, you know, you're all going to race home right now. You're going to open up your Xbox app right when you get out of class or something. So guys, the question is this a right angle? Is this a right triangle even? And so the way I do this, I just like so. Square this. Now, squaring, by the way, can be distributed over multiplication or division, not in the case of addition or subtraction. So let's see, 15 squared, that's 225. 36 squared, I'm not familiar with that one. 1296, that feels vaguely familiar. 4 squared is 16 times 95. Right, so I can cancel out the square root and I can square the 4 and get the 16. Add 1296 and 225, I get 1521. What is 16 times 95? Question? All right. Oh, what? Oh, so close. Yeah, question. Yeah, yep. You can distribute the squares, so I square the 4 and I square the radical, and then I multiply their outcomes. Yep. Yep. All right, so converse of the Pythagorean theorem. But guys, not only can we check to see whether or not a triangle is a right triangle or not, we can take this a little bit further. Did you know that? Did you know that, guys? Guess what, guys? We can take this further. What? With pit? With like a pit? Python pit, maybe? I'm going to remember this forever now. It says, for any triangle abaca where C is the length of the longest side, the following statements are true. If the hypotenuse squared is less than, all right, less than the sum of the squares of the shorter sides, then it's acute. Imagine this. If this is less than, that means the hypotenuse got shorter and this angle got smaller. All right? So it would actually be an acute triangle. If the C squared is larger, that means the hypotenuse got longer, right? Longer, and the angle got bigger. And if anything bigger than a 90-degree angle is going to be obtuse, in a triangle anyway, because it can't be more than 180 degrees. So you can actually use this as a test to determine you know, what type of triangle we're dealing with. Is it acute? Is it obtuse? Is it right? Are we getting distracted with the scissors today? We might lose our scissor privileges. So, verify the segments with the lengths of 4.3 feet, 5.2 feet, and 6.1 feet form a triangle, and then is the triangle acute, right, or obtuse? What do they mean, verify that it forms a triangle? How would I do that? From like a few chapters ago. Is that, yeah, it must be greater than the other side, right? Yeah, I think that's the only ones that I'd worry about, right? Is, whoa, ouch. So 4.3 plus 5.2, 9.5 is greater than 6.1. Yeah, these form a triangle. And now the question is it acute, right, or obtuse? So this is my hypothetical hypotenuse. And let's find out. So 4.3 squared plus 5.2 squared, is that equal? Or actually, we don't know what it is. I'll just put a box here. Right, I'm going to check for equality. I'm going to check for less than or greater than this, 6.1 squared. So let's check this out. It turns out this, to skip forward in time, is 11.3. And that is not 4.3. What am I saying? Here it is. Aha! I'm just going to cheat and not plug this in a calculator. 18.49 plus 27.04 compared to 37.21. All right, and this adds up to be 45.53, which is bigger than 37.21. This was my C side, right? That means my hypotenuse, my hypothetical hypotenuse, was less. It was smaller than. So what type of triangle must this have been? Acute. Okay? All right. Well, thanks for watching, Internet friends. Have a great day.